In this interactive simulation, we do a degree of freedom analysis for a distillation process. And the simulation is set up where we can do analysis around just one part, like the condensers I've shown here, and that's selected with this button. And the blue values correspond to unknowns, the mass flow rate and the mass fraction. And the mass fraction here of the liquid. And so the number of unknowns is listed, the balances, two species balance, and then a relation from phase equilibrium between this mole fraction of vapor and this liquid mole fraction that's assumed to be in equilibrium. And for these conditions, we've selected the number of unknowns. It says the system can be solved. We have the option of a partial condenser or a total condenser, so that we condense all liquid, and means this mass fraction here would be the same as this mass fraction here if we had a total condenser. And then the simulation allows us to click new problem, and we have different unknowns, so we're solving a different system. And we can do a balance now around the distillation column, the reboiler, or around the whole system. And we'll see how we do that when we look at the interactive simulation.
So here we're looking at the interactive simulation, and we selected the condenser. We have the option of the column or the reboiler also, or an overall balance. The blue are the unknowns, so this is a mass fraction, vapor coming in, mass flow rate leaving, and then this mass fraction of the liquid that's condensed. So we have three unknowns. We have two species balances because we have two components, and we have the additional information from vapor-liquid equilibrium that relates the mass fraction in the vapor to mass fraction of liquid. So this says we have no degrees of freedom, or in other words, this problem can be solved. And this is what the degree of freedom analysis does to tell us whether we can now sit down and calculate the unknowns, the blue values. Now, if I select a new problem, what this does is create different unknowns. So now the unknowns are the inlet flow rate and the outlet flow rate. These mole fractions are known. Again, this happens to be a solvable case. Now, another problem, a new problem, it's overspecified. We have three equations, only two unknowns, so it's overspecified. So we can do likewise. We can look at the reboiler. For these particular conditions, it's overspecified. If I go to new problems, now it's solvable, overspecified again, and let me decrease the number of unknowns and look at a new problem. Solvable for these conditions, and then overspecified for other conditions. Let's look at finally an overall balance. And now this tells us for this problem, the unknowns again are in blue. Change conditions. Let's increase the number of unknowns. Well, if I have 7 unknowns, now our system is underspecified. And pretty much for all the conditions we're going to pick, we don't have enough mass balances to be able to solve for this system. The other option here is to consider both A and B mass fractions as unknowns and have additional equations that say the mass fractions have to add to 1. And this is the case where basically some people like to do it one way, where they have both mass fractions unknown. Others like to assume we've already taken account that the mass fractions add to 1 and therefore only have for example, here, one unknown, not two unknowns. And so this degree of freedom analysis is valuable for understanding systems and how we can do mass balances on them. And depending on which part we select, we can have something that's underspecified or overspecified or solvable.